Okay, I'm back from being on top of the mountain and visiting a 7th century castle on our little outing today. The mountain was lots of physics and very interesting, and back here in the room before dinner to hopefully make this cast. So we have been talking about quantum mechanics, and we've been using a particular language. We have said that a wave function must be represented in some way. And that the same wave function can be represented in different ways. We could choose to represent it in x or p or eigenvectors of some operator. So the point here is we have this abstract thing that represents a system, and we call it a wave function. And we can then take that abstract thing that represents the system, and we can write it in different ways, in x or p or eigenvalues of some operator and so on. And so that's a very high-powered idea, this idea of abstraction and then writing it in some particular way without changing the physics. So we need a notation to do that. And the notation we're going to use to do that is called Dirac notation, after the famous Dirac. Dirac was one of the principal architects of quantum mechanics, and his notation is the sort of modern way of doing quantum mechanics. So this notation is called bracket notation, and you'll see what that means in a moment. So we start by writing a Dirac ket vector. Now notice ket is the second syllable of bracket. There's also going to be a bra vector that I'll talk about later. We write a ket vector psi like this. So this is an abstract wave function. It is not represented in any particular way yet. It's not written in x or p or energy or anything else. But it's a vector, and it represents a wave function. It's a vector in some space, but we haven't said what space yet. We haven't committed to a particular representation. So it's a way of writing this very abstract thing. It's a vector. It's in some Hilbert space. We haven't decided what Hilbert space yet, but we know it's a vector. Now, at this point, we can pick a basis or a coordinate system. So we're going to take this abstract thing, right? This abstract thing, and we're going to somehow cast it or represent it in a particular way. There are lots of ways we do this, and we pick the way depending on what it is we want to accomplish, what we want to calculate, and there are some problems that are easier in certain representations than others. So there's some experience that goes along with this, but the idea is that you take your abstract thing and you represent it in a way that you can calculate. So one of the easiest ones that you could do is you could pick a basis, the energy basis, and the energy basis are the allowed states, which represent the allowed energies, or with the allowed energies, for a particular system. So we write the eigenstates of the energy operator. So these are the allowed states, like we found in the problem that we did last week. And we write them as these i's. Now, you'll notice what I did here was I did a sum, right? I did a sum, and this term is really projecting the general psi, that one, onto a particular I. It's sort of like picking out the components, right? So this notation here, where I sum over ket I, bra I, that notation is really about projecting onto a particular set of eigenstates. And in this case, this thing right here is picking out how much of the wave function, the general function, is along the I direction. And that, in fact, we wrote before is just A sub I. Now, we have to do this sum because, remember, when we're going to take a vector and we're going to represent it in some kind of basis, we have to be complete about it, right? You can't represent three-dimensional vectors if you only have I and j. You have to sum over k too. So in this case, you have to sum over all of the possible states, and this sum is taking and picking out how much of it is along each direction. So these I here are the eigenstates of the energy operator. So what we did here was we wrote this notation and we projected, by doing this sum right here, we projected onto a particular basis. And now I would say, well, okay, when I interpret this A sub I is the probability of being in the I state. And we're summing over them with certain probabilities. Okay, we'll go on. All right, we should really talk about this this I notation that I used. So what I'm really saying is that very generally the Schrodinger equation is that. So there's some energy operator that acts on eigenvectors, and it produces eigenvalues in the same eigenvector. This is really the Schrodinger equation when we write it out. So we picked out these i's to project onto. We picked out the Hilbert space. We picked out the particular set of eigenstates. Now that we made that choice, we know what to do. And we had to sum over all of the I because we didn't want to miss anything. So that's an example of an easy case. So you have this notation where you start out with the vector as the generalized state, the psi as this abstract thing, and then you do that projection by summing over ket I, bra I, and that picks out these components, and voila. Now, what if you wanted to do a projection onto X space, configuration space? It's a little different because it's not a finite sum, right? Any of the x's are allowed in principle. So instead of doing a sum over all of the states, we do an integral over all of the states. And now, if we look at this expression right here, this thing right here, right, that thing, let me write it over here, that becomes our old friend, the wave function now expressed in terms of x. So we picked a basis and we projected onto it. And this is how we do it. So what you were doing in modern physics was this. You've already done this. Okay, so psi is our normal everyday wave function. Now I want to emphasize that that was a choice that you made. Okay, you could have chosen instead to project onto a complete set of momenta, and then you would write, in fact, this thing, that projection onto P, project onto P, and I get this wave function. That would be psi written out in terms of momentum. And there are places where that might be, more convenient. And one of the things that's nice about momentum is momentum is conserved. So some problems, it's going to be more convenient to write a momentum space wave function. And you need some kind of momentum space Schrodinger equation then. So we've taken our abstract psi, and then we've projected it onto an x or a p or maybe an I basis. And we did it with either this integration or the sum that we wrote like so. So sum, integral, or integral. So in fact, what you're really doing when you sum over these bases is these things, these sums and integrals are really just acting like one. And when we do this sum, or when we do this integral, we're really doing what's called inserting a complete set of states. Right? So it's like summing over all coordinates. All right. Well, we wrote out this abstract thing, this psi ket vector, and we learned how to project onto whatever basis we want. Now, you might realize at this point, it's like, wait a minute. So if I can do that somehow with psi, don't I need to do that with operators? Couldn't I write operators, which are sort of abstract things as well, in a particular basis as well? And the answer is yes, we have to represent them in some basis or coordinate system. So we're going to talk about that a little bit. All right, let's see if we can get to our familiar Schrödinger equation using this Dirac notation. Okay, so you can argue, or I will argue, that the central quantum mechanical equation is energy conservation, and it's no more than the Schrödinger equation. And the Schrödinger equation, written in this abstract way, looks like H psi equals E psi. So this is really abstract. E is the energy, it's a number, and H is the energy operator. Well, we can write the energy operator in terms of the momentum operator and a potential operator. So H is P squared over 2m plus V. So when I write this Schrödinger equation out in terms of P and V, it looks like that. Now, I have not written P or V or psi yet in any particular representation. It could be in X, it could be in P, it could be in energy, it could be anything I want. This is very abstract right now. All right, let's put it into X. Let's see if we can get to the normal Schrödinger equation that you know. So we're going to insert a complete set of states. We're going to project. So I put in right here, and this should be, of course, dx, of course. So I inserted that complete set of states. And I want to pick out a particular x, so then I'm going to project on an x prime here. So I inserted 1 here, right? And that's what I get with that integral. And of course these are all integrated. Okay, duh. Okay, so my pen isn't great. dx. Okay, and I took this thing and said, oh, that's just a wave function written in terms of that variable x prime. Now, I distributed things here. So now I have this operator that's sandwiched in between a bra and a cat, operator sandwiched in between a bra and a cat. Okay, so what are we going to do with these operators? Okay, well, again, this is the notation. If we take this thing right here with the operator in the middle, well, we can say, well, that means that this momentum operator is going to be represented in terms of x prime and x, and then that thing still goes through. Now, it turns out that for operators like this, that bra-ket combination is a new function called the Dirac delta function. We do the same thing for the V. So V operator, abstract operator, sandwiched in this way, becomes V of x prime and x, x prime x, and I have that Dirac delta function. That Dirac delta function is a new function which you may or may not have done in modern. Okay, I'm going to use it here though. So let me review. We inserted a complete set of states, we projected onto x prime, we got these operators sandwiched in this way, we interpreted them as looking like this, where we're really writing the operator in terms of x and x prime, and we get these new Dirac delta functions that are appearing. Okay, we'll go on. Now what's the Dirac delta function? It's a curious function. It's sort of a spike. It's infinitely high and infinitely narrow. It picks out a particular value. So the main way that we will pick out or will define the Dirac delta function is in an integral. If we integrate a function f of x over the interval a to b, f of x, and then delta function x prime minus x, well, what this function does is it picks out the value of the integrand, the f, at the point where these two things are equal. So the result of this integral is f of x prime if x prime is in between a and b, or 0 if x prime is not in between. So it's really quite simple. It picks out a spot. It's like a spike that picks out a value in the integration. It only has one value. So in our integration case, right, so we have our integral that we're, if you think back to the previous thing, we have this integral we're doing. And so what it does is it picks out when x prime and x are equal. So we end up with that integration looks like that. And the v x prime x psi, etc., collapses to that. So when we're all said and done, this abstract expression, when projected onto x, becomes that. Now that looks a whole lot like the usual Schrodinger equation. We've got momentum and we've got potential and x and so on. Now we have not dealt with that yet. Well, let's deal with that. We're really close. So one of the things that we know from quantum mechanics, one of the principles, is that we can take classical variables and replace them with, and I don't know what happened here, replace them with their classical, with an operator that's the same as the classical one. So v of x is the classical potential, so we'd rewrite it in terms of x, so 1/2 kx squared becomes 1/2 kx squared. This is the curious one though, p of x. How do we write out the momentum operator in terms of x? Now, we know the answer already. We know that it has to have an h bar in it because we know the Schrodinger equation. So somehow Heisenberg is going to have to insert himself into this. It turns out, and if you go online and you look at, derive momentum in terms of x, it turns out that this is really quite a hard derivation. It's quite subtle. I'm not going to go through it because I don't think it really adds a lot at this point. I really want to be able to move on. So I'm going to simply assert that we can write the momentum operator in terms of x like so. And again, it's very interesting to go read how this works. It's quite subtle. One of the nicest derivations has to do with the translation operator and how you move things and so on. It's really quite beautiful. I don't want to do it right now, though. We might come back to it if we have some time in the semester. Okay, so we now have the momentum operator. Let's go and put it all together. So when we put it all together, look what we have. Right? It's the Schrodinger equation. So we started with that really abstract thing, right? H psi equals E psi. And then we projected onto a complete set of states, and we inserted that integral, and then we identified how the operators work, and then we end up with this. Right? But that Schrodinger equation is completely a product of, it's a representation in a particular way. It came from the fact that we chose to use x. We could have chosen to use p, and then we would have gotten some kind of Schrodinger equation in terms of p, not x, or some other variable maybe. So we took the abstract and we made it concrete. Okay? That's really cool, right? Because it means that you can choose to write and represent the Schrodinger equation in any way that's convenient to you and convenient for calculating. Now there's some notes that I mentioned already that I should somehow talk about. So when we write the psi with the angle bracket to the left and so on like this, we call that a bra vector. Get it? Bracket notation, bra and cat, bra vector, cat vector. Yeah, it's a little too cute. And then if we do this thing, we do this representation like that, we project onto x. Well, when that operator, that ket vector acts to the left, you get this star here. So the star enters when you have that x acting to the left. Right? That's where the star comes from. it's probably fun at this point to do an expectation value. So look, the expectation value of an operator omega, right here. We write it abstractly like that. We sandwich it in between a bra and a ket. And this is the expectation value of that operator. So then we insert complete sets of states, right, here and here, and we integrate over both of them, double integral. Okay. And once again, we get this operator thing. Okay, but that operator thing that goes as x and x prime really goes as this. It's the same as the other operators we had. Now there's some interesting things that go on. Do all operators have to look like this? Do they all collapse to that? The answer is no. There are some very interesting operators that do not collapse in our x and x prime. We won't do anything in this course. They're called non-local operators. Every operator we're going to deal with in this course looks like this. So we put this in and integrate, and because of the integral, the properties of the Dirac delta function, one of these integrations disappeared. So we're left with, yes, that's right. That's the expectation value when we've represented everything in terms of x. Now, that was a choice, right? We chose to do that. Could we have done it in terms of p? Yes. Could we have done it in terms of some other eigenvalues, eigenvectors of some other operator? Absolutely yes. There's a question of convenience and ease of calculation. You start with this abstract thing and then you make it concrete. Okay, you'll probably have to run this a couple times, maybe more than a couple times. It's a complicated idea.